ladies and gentlemen. Today we are talking about section 5.3, and that involves using angle bisectors, specifically angle bisectors of a triangle. So we're going to start with, before we talk about the theorems, we're going to start with the definition of an angle bisector, which is a review. We talked about that way back in Unit 1, towards the beginning of the school year, which says that an angle bisector is a ray that divides an angle into two congruent halves. So in this picture over here, when we're talking about the theorem, we have an angle, angle CAB or BAC, and it's divided into two equal halves, as marked by these congruent markings, by this ray. So ray AD is considered to be our angle bisector. Now, angle bisector theorem is similar to the perpendicular bisector theorem. It states that if you have a point on the angle bisector, then it's equidistant from the two sides. So any point on this red angle bisector will be equidistant to the two sides of our angles. So in this case, the length from D to B is congruent or equal to the length of DC. We say equal when we're referring to length. If we're referring to these segments that I drew here, we would say congruent. So that's the angle bisector theorem. Those two lengths will be equal. Now, whenever we're measuring a distance, we always need to measure it perpendicularly. That's why we see these right angles here. So the distance from D to B must be measured as a perpendicular segment. Same thing with D to C. They have to be perpendicular. Otherwise, it's not an accurate measure of distance or of length. Just like when you have your height measured. You measured your height as the distance perpendicular to the ground. So from your bottom of your feet to the top of your head, perpendicular to the ground. Your height isn't measured at a slant. It has to be perpendicular. Now, we also have the converse of this bisector theorem, which says that if you have a point that's inside this angle, so point D, and it's equidistant to the two sides, as this is shown, and again, distance is measured perpendicularly. So if D is equidistant from the two sides, then it's going to lie on the angle bisector, which means that AD must be the angle bisector, so these must be equal. That's the converse. So the original, if it's on the bisector, it's equidistant from the sides. Converse, if it's equidistant from the sides, then it's on the bisector. Remember, the converse, you're just switching your if and your then. So that's the bisector theorem and its converse, and we'll use those to solve some problems. Here, the question is asking or telling us to find the measure of angle GFJ. GFJ is this portion here. Well, we don't know what this whole angle is, so we can't determine it that way. We don't know automatically if it's an angle bisector, but let's see if we can deduce that using some reasoning here. Well, we know that J is on this ray here. And J is equidistant from the two sides because they're both 7, and yes, we're measuring this perpendicularly. So that means that J is going to be on the perpendicular bisector, which means that FJ is our perpendicular bisector. So my reasoning is that J is equidistant from the sides. That's point 1. Point 2, that allows us to say that since it's on FJ, FJ is an angle bisector. And that means that these two halves are congruent. So this is also 42 degrees. So for our conclusion, we can say the measure of angle GFJ is 42 degrees because it's on the angle bisector. We know that's the angle bisector because J is equidistant, and that's using our converse, which we just talked about on the previous page. So here's an example of how we can use some reasoning to determine if something is on the bisector to solve a problem. Let's look at another one. For what value of x does P lie on the bisector of angle A? Well, if P is going to lie on some imaginary bisector of A, it needs to be equidistant from the two sides. So P must be equidistant from B and C. because of B and C, that's where we see it's perpendicular, and we need those to be perpendicular. So that's going to mean that those two lengths, x plus 3 and 2x minus 1, are equal. We can subtract x from both sides, so 3 equals x minus 1, and add 1 to both sides, so x must be 4 in order for P to lie in the angle bisector, because we need those two lengths to be equal. Well, let's check our work. If we plug 4 back in, this gives us 7. If we plug 4 in down here, we get 7, so it checks out just fine. It is equidistant from the two sides. Let's see if we need to go through any more of these. Let's look at number 4. Do you have enough information to conclude that ray QS bisects that angle? Well, here we don't know if the two halves are congruent. We do know that these lengths are congruent. So one might be tempted to say yes because S is equidistant from the two sides. However, we can't use that because these aren't perpendicular. We have to measure distance perpendicularly. So in this case, we can't say it's equidistant because it's not being measured perpendicularly. So in this case, no. And I just gave you that verbal explanation, no, because our distance isn't being measured perpendicularly. If it was, and it was something like this, we could say sure, it's equidistant, same length, perpendicular. But in this case, it's not, so we can't. If we knew that these were equal, we also could say that it was the angle bisector by the definition. It's dividing something into two congruent halves. But in this case, we don't have either of those two cases. Now, if we have a triangle, and we have 3 angle bisectors in this triangle, they will, all these 3 red ones, which I'll trace, no, I'm sorry, the red ones. These are our angle bisectors, and they all meet at a common point P. That point is called our incenter. The incenter is where our 3 angle bisectors meet. That's our point of concurrency here. And the theorem says that P is equidistant from our 3 sides. Well, if we look at this piece by piece, we can see how that's logical. If this is the angle bisector, then it's equidistant from these 2 sides. And if this red line is an angle bisector, then P is equidistant from those 2 sides. So we can see it's equidistant from all 3 sides. That's theorem 5.7. Point of concurrency of the 3 angle bisectors, which is called the incenter, is equidistant from the sides of that triangle. Let's do a problem involving that. Here, n is the incenter. Find the length of ND. So that's what we're looking for. Well, in this case, we don't know what ND is. I'll go ahead and call it x. But if n is the incenter, I know it's equidistant from all 3 sides. So I can call all 3 of those x. Well, I don't know what any of those are, so that's not going to help me out. But I do know that I have a triangle here that is a right triangle. Since this is a right angle, so is this. So I can use my Pythagorean theorem to solve for this missing side. My Pythagorean theorem says that c squared equals a squared plus b squared. C is referring to our hypotenuse, which in this case is 20. It's our longest side, and it's across from our right angle. And a squared and b squared, I can say, are 16 squared and x squared. Doesn't matter which one you place which, because since it's addition, the order doesn't matter. It's our commutative property. And now we can solve this equation here for x. If I square them, I end up with 400 and 256. I'll subtract 256 from both sides, so I end up with 144 equals x squared. And so I know x must be 12 if I take the square root on both sides. So in this case, ND is 12. Sometimes you'll have to use the Pythagorean theorem, like in this case, to solve for a missing length. If we were told automatically that this was 12, then I could say, well, I know these are equal, so this has to be 12 as well, and so it is this. But in this case, we had to take a little bit of an extra step. The last bit of information that's important to know, just for vocabulary's sake, is let's say we have a triangle with our 3 angle bisectors, if I were to choose that in-center as the center of a circle, then I can draw what's called an inscribed circle. This circle, the center is at our in-center, and the circumference of it is touching the edges of our triangle. It's called an inscribed circle because it's found inside the triangle. Whereas last time we had a circumscribed circle because it was drawn around the triangle. And those are some important vocabulary words that we will talk about a little bit later in the spring, but it's time for a nice introduction to that. So this is called an inscribed circle starting at our in-center. That concludes section 5.3. The textbook assignment is posted on Edline, and I wish you all the best of luck in finishing your assignment with this. Questions, as usual, feel free to contact me.